the 5-year rate is 16% for survival. And that's really actually way down at the tail end. I mean, it sounds really horrible, and it is. But it varies. And so there's these other stats in the other table. It's the 5-year non-small cell lung cancer, NSCLC survival rate, that has it stratified. You hear about your data stratifications, stratified by the stage of diagnosis. And so you hear, that the 16 years, 16% make it to 5 years. Well, that's right out here. It looks like there's a whole bunch of other people that, if you were diagnosed early, diagnosed in stage 3, that you've gotten to stage 3, that the 5 years is the bad news, that it's not a 5-year survival anymore. And I think you would want to know. I would think you'd want to have this information to say, instead of, my father was diagnosed with stage 4 non-small cell lung cancer, and was told, get your affairs in order, you're probably only going to live another couple of weeks, maybe a couple months. Turns out he lived another 3 years. Because the doctors are trying to give you a single number, because it's easier for them. But they could take into account that someone is in good health, is, for many cancers, your age at diagnosis, your overall health at diagnosis. My father was diagnosed as a consequence of not recovering quickly from knee replacement surgery. They had thought that he was in good enough shape that they gave him new knees. And then they diagnosed him with stage 4 lung cancer. And so he was actually in pretty good shape, and he had perfectly good quality of life up until like the last 2 weeks of his life. You can't tell from just a number, just 16%, not going to happen. You need more information. And a distribution, whether it's a easily mapped one, probability distribution, or just more information like this, provides valuable news to you. The other thing is, it's part of the acceptance thing. Because people worry about unlikely events and are surprised by unlikely events in other cases. And one of the things, like I said with the acceptance, is that you can practice knowing which things count and try to tell yourself the way the book that this stuff comes from, or there's actually been a book written, Don't Sweat the Small Stuff, and it's all small stuff. You can choose what risks you worry about. You can say that more people die in automobile accidents than by aircraft accidents. Fatalities per 100 million passenger miles, even though planes fly a really long ways. Very few people die of aircraft. Lots of people die of cars. Buses and trains are about the same. Share a ride. You aren't going to die. It's like so those things, being aware of those and saying, this trip to the store is just as important to my life as the trip to the plane. I should be just as ready for something bad to happen on this trip to work tomorrow as I am making my vacation to Europe in 3 months. But we tend to behave differently, and so having a sense of the likelihood of events helps you deal with things and be more ready for things that could go wrong. So, one of the things people say when you try to tell them to use larger volumes of data, to think about the larger data set, is they'll say, well, the law of, they'll just say the law of large numbers, because sample averages pretty much converge to the expected value, which means you roll the dice long enough, you'll be averaging, the 3.5 that you really towards the expected value. They actually mean, it turns out there's a meaning for that mathematically of convergence in probability. And I didn't write it down, and I'm not going to tell you that Wikipedia is actually a really great source for this. And then there's the central limit theorem, which people think means that everything's got about the average. What it means is that if you have a large group and select a reasonably large subset from that group, so at least 30 members, and find the average, even if you get different clumps of 30 people from all over, the averages of those groups will form a normal curve. That is, it'll be a symmetric curve with mean, mode, and median all at the same place. And that's all that's really saying. It doesn't mean everything that average tells the whole story. So, our good friend, the Gaussian curve, the bell curve, the normal distribution, is, as I just said, it's symmetric. Mean, median, mode are all the same point. Normal is usual. Normal is normal. We have a sense of what things are normal. We notice when people are too tall or too short. The rest of the time, the height is not noteworthy, but there's still a lot of variation. But we don't notice it because it's normal. It's only people out at the ends of these distributions that we really notice as being something other. And people are good at that. A lot of animals are good at that. Something recently, I don't remember where it had been reported, one of the free-range chickens have a higher death rate than from not being eaten. They have a higher death rate than caged chickens because chickens peck the bottom of the pecking order to death. And the ones that chickens that are at the bottom of the pecking order are usually different. And one of the things that makes people special is that we can learn to take away the animal instinct part and treat somebody different as part of the population. And that's really what we're trying to work on. We're part of the population. The symmetry and the part where the total population is pretty much described within 5 sigma is what makes a normal distribution normal. It's not necessarily the height or the width or the actual, it's the symmetry and that the distribution, the shapes having most of the having the coverage that it does. It's the area under the curve. And I'm going to ask you to go back, because I just remembered something else I wanted to say on that slide. One of the things in being a Six Sigma black belt and trying to work to improve processes and stuff at companies is if people are complaining that something takes too long, it takes too long. You better fix it. It almost certainly is taking longer than the project plan expects it to take. And you will almost certainly find your project losing money if you don't fix it. And that's because we have a good sense of how long should it take to run a test of this software? Well, nobody just knows offhand, but they'll test their software and they'll say, this is taking too long. And they'll know. And if somebody says that, it's an opportunity for improvement. This is actually easier to see than I was thinking it might be, but it's still kind of hard to see. What we have here is the central lines and then two shaded areas, and I'm going to be blocking this thing a great deal, but there's a central shaded area, and then there's a lighter shaded area outside, okay? And here in the winter, they overlap because each one of those is like a little cross section of a normal distribution. So the distribution on January 17th that's marked there, the average high is 40, but a normal value for high is anywhere between 55 and 30. So when we don't get average temperatures, we'll get people on the news radio saying, we're colder than average today, but we're not so cold that it's not within normal. And so we could still, we're actually going to have some record lows that are outside the 2 standard deviations this coming week. But mostly we get normal weather. We don't actually get average temperatures very often. We get normal because we have a lot of variation in our weather. Year to year, whatever. Shall I talk in this? Okay. I will talk at the microphone. And finish up this slide because all I was really going to say is that the temperatures are not just an average. The normals are a much wider thing, and we should just learn to live with it. And the expectations, maybe for things that aren't normal, still usual. Poisson distributions describe occasional independent events, things that happen with some kind of rate, but not consistently. Soccer goals happen, 2 per game or whatever. Calls to a call center, so many per hour. But the arrival rate, the time between them, isn't even. And the time between them is what you use the Poisson distribution for. And so what you want to do is not plan for them to be even, but plan for them to be varied like that so that you don't have too many people waiting too long at the call center, or that you're equipped to handle that, or that you're equipped to handle things that happen at this uneven rate. And you can use this kind of distribution to plan for that. And that's what these are for. So the overflow flood is like the snow circumstance we've had, where there's every 100 years, there's this many inches of snow at once. Do you want to bother spending tax dollars on equipment that might get used only once every 100 years? Or just get out and get to work the next day? Or do you want to say, yes, in these 100-year events, even if 3 of them happen in one 10-year period and don't happen for the rest of the 100 years, I will make sure to have plenty of hot chocolate mix at home, and I'll just sit there. So it helps you predict and helps you react and helps you plan to have the additional information and use the distribution. Next slide. And here, the one on the right is that bathtub distribution I mentioned. There's actually 3 distributions added together. The things go wrong when they're first manufactured or first used or whatever, or infant mortality, things like computer chips go bad and begin if they've got some manufacturing problem like electrostatic discharge or something like that. You find it early on, die as soon as you turn it on or pretty soon after. There's a certain number of types of failures that will happen approximately constantly, randomly throughout the life. And then there's when things wear out. You add those together and you get this just this scoop type thing that helps predict your failure rate. And if you're in the business of repair, if you're in the business of replacement or something like that, knowing this kind of thing helps you make your plans. You can learn what the rate is for your product and plan accordingly. And that is also done in the Weibull distribution, which you can see down there on the lower left, has several very funny shapes. And those are shapes of the occurrence of failures over time. I think it's over time. Over time? But occurrence of failures. The Rayleigh distribution used in predicting software defects is a special case of the Weibull distribution. And so the people who develop software commercially and who are developing software that has to have very high reliability will see where their defect rates are coming out. They don't use it. The average defect rate doesn't mean anything because you're trying to get yourself it actually, for the defect rate, so Rayleigh is kind of in between this one, the green one, and the purple one. And it's got a steeper slope on the back end. You're going to be trying to tell when you've passed your peak, because then you can predict by how long it took you to reach your peak and get past it, how long it'll be until you have reached a defect density at which you can release the software. And we used it in very reliable embedded software for satellites, and it really works. It's amazing, but yes, software defects do follow Rayleigh distribution, and I kept wanting them to be following another distribution because I kept seeing that, gee, we have more defects than we wanted. But we were following that Rayleigh distribution, and once I accepted that, I could plan when things would be done. And I could plan across several different groups of software developers. Some were reusing software from another satellite program. Some were developing their software very closely with the hardware people and testing it all the time. And they would have a very low defect rate. And so did the used software people have a low defect rate. Then there are the people who are developing brand new software for brand new hardware, and the hardware team was a little farther behind. And they had a higher defect rate. And yet all those curves, independently and added together, still came out to be Rayleigh distributions, still good for predicting. Political predictions are all using distributions. They stratify. You know, they'll say that a particular candidate is ahead of another by some number, and then they'll clarify it by saying voters 18 to 24, because they know that saying this candidate is, you know, the third best candidate doesn't really mean anything if their probable voters aren't going to show up to the polls in that area. There's a lot of data that goes in there. Average sizes, women shoe sizes there. American women apparently average a size 8 these days. Obviously, shoe companies make shoes in lots of other sizes, because making the average size shoe doesn't actually, I mean, it's a lot of the women do wear that. It's kind of interesting looking at these charts. The men's shoe distribution was actually a lower, wider distribution. The women's shoes did tend to peak right there at the average a lot more. I, of course, have been looking for 9.5s and wondering why they aren't out there. And I'm glad that I don't wear an 11.5. So it makes business sense, it makes social sense to continue to think in distributions. And so I'm going to continue to advocate that people think in distributions and just ask themselves some questions. Are you limiting your information by thinking in averages? Are you missing something important? Are you getting the information? Is someone limiting the information that you're getting? A book that I put on the next slide called A Mathematician Reads the Newspaper talks about the questions that some of these things raise when you start thinking about the probabilities. Probably aren't really going to think a lot about the average weight of salmon, but I'll tell you, I'm pretty sure salmon aren't born at 2 pounds. So is this average weight of salmon only salmon that they caught? If they, which is likely, obviously. Does that mean they didn't even try to catch the little ones? Did they not count them because they weren't supposed to have caught them if they caught the little ones? Oh no, we threw that one back. We didn't actually ever have it. Were these all spawning salmon, so they were already up in a river rather than out in the ocean still. I mean, where did this data come from that this happens? Did the heavier salmon, I mean, do most salmon go up, if it's spawning, then most of the salmon spawning are between 6 and 8 pounds. And the ones that got larger happen to be, you know, lucky fat salmon, because of course salmon die after they go back upriver to spawn. So most of them get big enough to spawn, go spawn, and die. So there's a lot more to the story than to say that salmon have some kind of average weight, and that's the average weight of salmon. And there's things in the newspaper where if you read them thinking about this kind of thing, you'll realize the average this, the average that. There's not the whole story there. So, again, I recommend Wikipedia. It's not supposed to contain original content. You know, it's supposed to be an encyclopedia collecting information that's been published other places. But the write-ups themselves are usually, for things on the probability distributions, are actually much better than what's in their sources. They're clear, they're brief, they're to the point, they have the nice pictures, they have copyable math. Very nice. And then about the critical thinking, I mentioned A Mathematician Reads the Newspaper. My edition is the 1995 edition. They had a new edition come out 2013. John Allen Paulos has written other things about including math in your daily life. I'm just about done. I want my chocolate mousse. About learning to question some of the things you get with the things you already know. Pretty much all the quality people know these things. And for a lot of quality people, using the average is a shortcut. And I'd like to encourage you not to take that shortcut. Take the long way and get the big view. And so I'm done. Things like employee satisfaction and engagement surveys are very subject to how they're written and immediate concerns at the time. Now, the companies that publish those and prepare those for companies to use have a lot of statistics on what can be expected. You can actually go out and visit the Gallup site, which has a bunch of data on engagement surveys and the results of engagement surveys overall, things like that. They have studied how to word their questions. It's actually a good reason in some ways to buy a professionally worded survey than to try to build your own, because you do get different results, and you can write the questions a certain way to get certain kinds of results. You'd be designing your survey to receive a certain shape. Oh, okay. The question is do results from employee engagement, employee satisfaction type surveys follow any particular distribution as a rule? Are they written, since you can write them to get a particular distribution, are they written for any particular distribution? I don't know. I did not actually look that up when I was looking at some of this. I did see that they had that information out there. So I'd recommend doing something like going to the Gallup site or something. I'm going to say that it's probably written to be normal. They are trying to get a normal distribution. So if you have a shifted curve, then you should, in fact, take that as a sign that depending on the direction of the shift, that you have a noteworthy result. Because I do not believe that Gallup or Gartner are also consulting in how to improve your employee engagement. Are they? Okay. If they're doing that, then they're writing it for a shift. I would. I mean, that's you can, with surveys and things, you can write things to get a particular result. And people do surveys all the time, very informally, and small wording changes can make a big difference. They aren't terribly scientific.
My experience with those types, it usually occur after some type of an event. And it's usually a bad event, and then they get what they anticipate to be the answer. So I think it's not random enough to really gauge a good health of what they're expecting. A bad event occurs, they go here, yeah, we know it's bad. Or we know the morale's down or something like that. And then they can look at attendance records and figure that out too.
I think we all want dessert. Thank you.